So in question 4, we've got to show that the differential of x squared is equal to 2x, and we've got to do this from first principles. I'm sure you've seen this before, but here's the graph of x squared. I've got 2 points sitting on that graph, A and B. If the x-coordinate of point A is x, the y-coordinate here will be x squared. There is a gap of h between the two x values of A and B. This will be x plus h, and this will produce a y value of x plus h squared, because the function is simply x squared. And just before we start the actual proof, the gradient of AB, which is the rise over the run, the rise will be x plus h squared minus the lower value, and that will be divided by h. And the trick is that we're going to be moving B towards A all the time, so h will tend to go to 0, and we have to work out what this expression will go to. So this is specific to the graph of x squared, but there is a formula for the general situation to form the differential of any function, and it's this. It's really saying exactly the same as this. So once we've plugged x plus h and x into our function, which is x squared, I will get the same expression as this, but let's just try it. And indeed, as expected, that's what we've got. So we need to expand the top line. Here's the expansion of the first bracket, negative x squared tacked on the end, and the x squareds cancel. And that's one of the reasons why when we differentiate, the power keeps dropping down by 1. And also we can cancel an h. And what we're left with is the limit as h goes to 0 of simply 2x plus h. Well, if h goes to 0, this term will disappear. So at the limit, the differential of the function x is equal to 2x. And this, of course, indeed is dy dx. And that's the answer to question 4.